The button is
Right.
it.
We begin with a word of prayer.
Very good.
Dear Lord, thank you for this day. Please help us today as we learn about algebraic topology. Help me as I present this material. Amen.
Amen.
So, last thing we proved, let's see here. It's theorem 3.6. If x is path connected and x naught, x1 are in x, then pi 1 of x comma x naught is isomorphic to pi 1 of x comma x1. So essentially that, without loss of generality, we can consider, well, essentially any two points in a path connected space where in the same path component have the same fundamental group. So next few theorems and corollaries, we're going to be going over more technical theorems like that that'll give us more information about the properties of the pi 1 functor.
It's kind of funny, like, it's the fundamental groupoid, right?
Yeah.
But then that result kind of sort of undoes that, right? Because it says that
Yeah.
the choice of point is sort of irrelevant.
Yeah. I mean, if you're thinking of a set, like a groupoid in the category of sets is just an equivalence relation.
Huh.
Because the morphisms there are just bijections.
Ah.
So, I mean, essentially, for any groupoid, no matter what category you're working over, what category the morphisms come from, it's going to squash everything in the same equivalence class, that you can reach by one of the morphisms.
Uh-huh.
It's going to squash down to a point. So essentially, you're just going to get, these disjoint groups, essentially, if you want to think about it that way.
Huh. Cool.
So, products. We're all familiar with the set theoretic product, which is just, A cross B is equal to set of all A comma B for A and B and B, which you can, of course, actually define in terms of sets. But usually we just say, okay, it's pairs. But what that means functionally is we have these functions, right? From the direct product to each of the components that give us back each of the two slots, essentially. Right. So using that same idea, you can develop products in other categories. So here in the book, he talks about products in top, but I just wanted to give a slightly more general viewpoint of those. So you can see I have the definition here. If C is a category and you have two objects in that category, then this object here, A cross B, together with these two projection morphisms, forms a product if this diagram here commutes for unique morphism alpha beta. So
that's the product category?
Right, and essentially this morphism here, if you have some topological space H and functions, continuous functions of course, to A to B, then this is the product of those two functions. And that's sort of what characterizes these products. So our first theorem today essentially tells us that the pi 1 functor behaves well with respect to these products. So this is theorem 3.7. If x comma x naught and y comma y naught, I should probably move this chair here, are pointed spaces,
Continue on without me if I leave.
okay, then pi 1 of x cross y comma x naught y naught is isomorphic to pi1 of x comma x naught cross pi1 of y comma y naught. So let's see here. Essentially,
I love this theorem.
yeah.
Yeah.
So
Theorem is a joy to use on tests.
prove this here. We use P and Q, these projections, right? And essentially what we want to show is that this map here is, I'm not going to write the function type, but is an isomorphism between these two spaces. So if f is a closed path, at x naught, y naught, then P star, Q star, acting on F is equal to map induced by P acting on F, map induced by Q acting on F. Or in other words, the direct product of the path class of P composed with F and the path class of Q composed with F. And in the book, I found, I guess sometimes they do and sometimes they don't explicitly write the composition there, but this means P composed with F and this means Q composed with F.
Yeah, yeah.
So this is a homomorphism just by virtue of the fact that P and Q are morphisms in the category top, and therefore are continuous maps. Pi1 is a functor, so it sends these to homomorphisms. So essentially all there's left to show is that this is in fact an isomorphism, then we've shown the theorem. So essentially they just define this theta map, which maps path class of G, path class of H, to the path class of G comma H. Now, there's more to proof here. Essentially, they just defer it to an exercise. They say exercise 3.5 shows that theta is well defined. So, just to recap, exercise 3.5, to show you what that says. Exercise 3.5. Essentially, all it is if you have f naught homotopic to f1 rel I dot and g naught homotopic to g1 rel I dot,
Yeah.
then
Typesetting's a little dicey there.
f naught g naught. What are you looking at it in the book?
Yeah, you can hardly see the dot in my book.
Oh, really?
But it's there, but...
Well, I think it's like that normally. Like the
Yeah.
dot kind of blends into the I.
Okay.
So their I dot kind of looks like I dot.
It's like a magician's
Like a
eye.
stick.
You're trying to shoot the dot off the top of the eye.
Yeah.
Stick figure.
But so f naught comma g naught is homotopic to
Stick figure?
f1 comma g1.
Yeah, you're right.
Rel, I guess. Well, yeah, I guess still rel I dot.
Huh.
So I'm not going to get into proving that, but that's essentially what it would take to finish the proof.
It's probably like the things we did last class.
Yeah. So let's see what we have next.
So that's... So once you have that, that proves that...
So that's theorem 3.7.
So
That
would-
proves that this map is actually well defined, is the main thing. And then once you have this, just by looking at the formulas, it's pretty easy to see that this is in fact an inverse of this product of the map induced by P and the map induced by Q.
Okay. See, this is really,
Because like the PF and PF, QF is actually just going to be F.
Right, exactly. This is going to return the first component, the second component, which is going to be GF. Or I mean, GH. Exactly.
See, this is a really nice theorem, right? For example, once we know the fundamental group of, say, the sphere, or let's say the circle, and then the circle, then this gives you that the fundamental group of the torus is just the direct product of the fundamental group of the circle and the circle as an application, and so much more. It's very useful.
Yeah, I don't know. I was looking up some terminology when I came here, and that's why I was reading a Woody book. I want to say, I think there's actually a term for this type of functor. I think maybe it's Cartesian functor.
Huh.
I know if you have a category that has all finite products, it's called the Cartesian category, so... But I'm not sure on that terminology. So this next lemma here, let's see. I guess I'll erase.
3.8.
Well, I can do over here. So lemma 3.8. This is kind of a technical lemma, and if you're looking in the book, you can see that they use the picture argument again.
Yeah.
But I'm actually relatively excited about this lemma because I actually sort of understand their picture argument here. So
very
hopefully
good.
I can explain it to you guys. Also, it has commuting diagrams, so bonus points. This is also one of the few places where we actually go back to using free homotopies again, so I guess that's interesting. So, assume that F is a homotopy between this phi naught and phi 1, where phi naught and phi 1 are discontinuous maps from X to Y. Then we choose X naught and X, and that lambda denote the path. Now this here is a bit confusing. I don't know if they use this notation before. They say f of x naught, and they just leave a blank. But essentially what they're doing here, this is partial application. I would write this just with an underscore, because that's how you do it in Haskell.
Or just
But,
write lambda of t is equal to f of x naught t.
Right, exactly. Or if you really wanted to, you could say lambda is equal to lambda t dot fx naught t, but that's a bit too computer sciencey, so we won't do that.
Yeah, that last thing you wrote seems wrong to me.
Yeah.
This?
Yeah, I'm pretty sure that's just wrong.
On principle.
Yeah, it's just wrong. Doesn't belong in my office. Get it off the board!
Oh, this is then.
Ah!
But,
How dare you?
But I did have a nice way of looking at this visually. So, if you have this here is phi naught, this here is phi 1, and this is phi naught of x naught. Essentially what you're doing here, instead of usually what we think of, we're varying the paths along one direction, and we're continuously deforming the path. We're sort of looking at a point and what happens to that single point under the deformations. So this path here is our lambda t. So with that in mind, we have a commutative diagram.
Huh. Interesting.
So essentially, we have the map induced by phi naught is equal to psi of the map induced by phi 1. So, oops. Or phi here, or psi. I'm gonna have to figure out how to not get those confused one day. But psi is the isomorphism that takes the path class of G, sends it to the path class of lambda G appended with lambda inverse. So essentially what this says is if you have two freely homotopic maps, right, then they're not the same necessarily, but they differ by this isomorphism here. So proof see. So, because these are maps, right? These are maps from closed paths to closed paths. To show that they're equal, we check that the value of each maps for every closed path are equal. So we let f from I to x be a closed path at x naught, and we define g of ts equal to f of little f of t comma s. And so this g here is a homotopy between phi naught composed with f and phi 1 composed with f. And they have this triangulation of I cross I like we've seen before. So essentially, the actual homomorphism, or not homomorphism, homotopy that we're going to construct is going to be a composition of this G homotopy and another homotopy H, which I'm going to define in a moment. So essentially, we're thinking about this as the domain. We're mapping it through the H map. Then we're going to apply this G homotopy, and that's going to give us the result we want. So this H map, of course, is a map from I cross I to I. So that's what I'm doing here. So this is how we're partitioning our domain. Our range we're partitioning, it's going to be a lot simpler. So down here, we're naming points. We got alpha, we got delta, gamma, beta, and here in the middle, rho. So the reason why I think this is easier than the other proofs by pictures that he does, you notice here these are honest goodness triangularizations, whereas before they kind of split the space into trapezoids. And the nice thing about triangles are they're simplexes, right? So essentially he's defining this H map and doesn't give a formula for it, but he defines it on each of the vertices of the simplices that make up the domain here. And that defines it everywhere in the middle. And that gives us a well-defined map from I cross I to I. And so, let's see. He says define h of a equal to h of q. He sends both of those to alpha. Define
Oh,
H of
this
V.
is slick.
Yeah, it was really cool once I figured it out. Equal h of p equal to beta. H of c. Oh, I lost it.
Yeah.
Wait, did I? H of p, gamma. And
D
H of D is delta.
D goes to delta.
okay, yeah, d delta r rho. Thank you. As I've mentioned before, I technically need to buy reading glasses. Probably would be helpful. Alright, so you got that as your definition, right? So essentially what that does for us, he piggies back off another homework exercise back in section 2, which I'm going to write down for you guys. Or I'll probably just read it. Yeah, because it's kind of long. Let A subset of Rn be an affine set, and let T from A to Rk be an affine map. If X subset of A is affine, or convex, then T of X subset of Rk is affine, or convex. In particular, if A, B are distinct points in A, and if L is a line segment with endpoints A and B, then T of L is a line segment with endpoints T of A, T of B, provided that T of A does not equal T of B. But if T of A does equal T of B, then T of the line collapses to the point T of A. So
it maps
essentially,
lines to lines or to points.
right, exactly. So if they're distinct points, it'll map to a line. If it maps to the same point, it'll just squash down to a point. So, without going through the details, let's see, I think this edge here gets mapped down, well,
Yeah,
Q to A gets mapped down to alpha.
right,
I think P to B gets mapped down to beta.
right.
And then the two triangles in the corners become this. Yeah.
Right. So, what's important though, what happens up here is, let's see, I should probably draw.
So the lower triangle is sort of a fixed triangle in some sense in
Yeah.
this.
This is our T direction,
Right, because all three of them.
this
all
is
three
our
vertices
S direction,
are fixed.
right? So at,
Oh, it's really, I can see it. I can see it.
yeah, see up here, this here is
Cool.
going to be our H of H of 0. Well, I guess H of t comma 0, yeah. So this line here, I guess I could probably use a different color for this. That'd be helpful.
You can
Get bonus points from you.
You can write, yeah, you can write, you can also write, like you got some white space above your proof, you can write in there too, without danger of confusion.
So, essentially the important part though, this line here, which is H of, I'll just get my
T1.
T1, thank you. I didn't know if it was T1 or 1T, but. And so this, if you work out the details,
So, whole thing.
is going to map here on the range. And this we're going to apply G to. So on this section here, applying G to this, which is f of little f of t comma s.
Yeah.
Notice t is 0. So in this section here, we get f of little f of 0 comma s. And that's equal to f of x naught comma s, otherwise known as lambda. Here, as we vary in the t direction, you get f of little f of t comma 1, and that is equal to phi1 of f. So I probably should have moved this over because now I don't have space here. But finally, on this section here,
Oh, you can erase that stuff. We know where the points go to.
okay,
Now. Yeah.
yeah, but at this point here, you're going to get f of little f of 1 comma s. Of course, this is a closed path at x naught, so this is going to be f of x naught s. And of course, s now is going opposite what it was before. So this is actually lambda inverse of s. You notice this actually is equal to, because of the 1/4, 1/2. It's not just a reparameterization. This whole path, once we apply Gmap to it, is going to be equal to lambda phi1 of f lambda inverse. So there are more details to verify, of course, like you have to figure out this is continuous, and you have to show that down here. Actually, I believe this just maps to the same thing. So that, I believe, should give you phi naught of f down here. Use a different color for that. So this here should be phi naught of f. So then once we define this J homotopy, J is equal to G of H, and then we can see J is a homotopy from phi naught of f and lambda joined to phi 1 of f adjoined to lambda inverse I dot. So therefore, stating this in language of path classes, essentially, running out of room here, I think I can still do it. Phi naught, map induced by phi naught, f is equal to path class of phi naught of f, which by this is equal to the path class of lambda adjoined with phi 1 of f adjoined with lambda inverse. For this here, in other words, side note, is just equal to, well, this entire thing, I guess, right, is equal to our isomorphism, remember, of the map induced by phi 1, because our isomorphism was just appending lambdas on the end, essentially.
Right.
So that shows it. So I think probably good to erase this now. Are you guys good with that?
Yeah.
Or do you have
Yeah.
any questions? Okay.
You could. Probably can erase your category.
Probably that. Oh yeah, we're not going to need that much in the future.
Erase it all.
I guess I'll start over here. Actually, I don't think we need anything that I have up currently. Alright, so building off this, we have a corollary. And this is pretty basic, so we probably won't write it. So the corollary is, if you have these maps, phi naught and phi 1, but they're pointed. So instead of going from space x to space y, they're going from space x comma x naught to a space y comma y naught. And if you have those freely homotopic, then 1, map induced by phi naught and phi naught of 1 are conjugate. That is, there is lambda element pi 1 of y comma y naught with phi sub naught of f equal to lambda
See, at this
times
point it's
f.
easier to write.
Yeah. Guess you got to say like path class of lambda times the. Yeah, I guess I probably should write it.
Do you want me to hold my book up to the camera?
That's fine. I can
Copyright
just write out
issues.
this last bit here.
Be careful.
So-
copyright issues. You never know.
So if we could just copy it, we'll just copy it.
Although I sometimes
F equal to.
But I also like, wait, should I do that?
I mean, it's simple once you remove all the details.
Is it fair use? I don't know.
Essentially, just conjugation in the group pi 1 of y comma y naught. So this of f path class of lambda inverse. So moreover, they're not just related by this isomorphism. They are actually conjugate in the group. And so essentially, all that's coming from is the fact that now these are pointed maps. So it forces all the computation to stay in the group instead of out in the group void. So that part's pretty basic. And that was part 1 of this corollary. So second part, well, pretty easily follows once you know some group theory. But if pi 1 of y naught abelian, then these maps, or induced maps I should say, are actually equal. And that of course just comes from the fact that once you get to this, you can swap it and then these cancel out and you just get f of the map induced by phi 1. So I'm going to erase that just so I have more room. Get full board space here. So this next theorem is very important. Theorem 3.10. If beta is a homotopy equivalence, then the induced homomorphism is an isomorphism. For all x naught and x. So this is kind of neat because it's almost sort of an argument by diagram.
Yeah.
So the proof here,
Oh, that's a diagram.
choose a continuous map alpha. So we got alpha here going from y to x with alpha of beta homotopic to 1 on x. So in other words, this is a homotopy equivalent. Oh, and of course we have to have beta of alpha homotopic to the 1 on y. So by the lemma that we just proved, the lower part of this diagram, or kind of takes a while to draw diagrams. How am I doing on time?
I think you're okay. It's 2:50.
Okay.
So you got till 3:40. At least for me, you do. Is that okay for you, Daniel?
Are you trying to get to the end of the chapter?
Yeah. There's some stuff that I can leave out at the end, like the stuff on topological groups, since we sort of went over that in topology. But I would like to at least mention a few things there, like some of the theorems at the end,
Yeah.
whether or not we get enough time to prove them. So this is one. And this is the isomorphism from our
You're almost to the first big definition here, in my humble opinion.
first big definition. You mean
Connected.
simply connected?
Yeah.
Yeah. So this is, again, they're omitting the composition here.
I mean, in some sense,
So
these
this is the
are
map induced by alpha of beta.
technical preliminaries. I mean, they're necessary.
Right, yeah,
Talk about
that's
it, of course,
what I
but-
said at the beginning. Like, pretty much everything until we get to,
So this is theorem 310 right now. You're writing.
yeah. I guess everything until we get up
So
to...
you draw that that diagram there.
Right, so by the lemma that we went over, bottom half of this diagram commutes. Since psi is an isomorphism, we also have that the map induced by alpha beta. It's an isomorphism. And why is that? Well, one's an isomorphism.
That's nice.
This is an isomorphism. It's invariable. So composition of these two is an isomorphism. This is an isomorphism. So the next part they don't really provide detail on, but one way of looking at it is it's just a set theoretic fact, which of course you could prove if you had the time, that if you have an isomorphism, equal to the composition of two maps, then the last one has to be injective and the first one has to be surjective.
Right.
But an interesting thing in the categorical context is it's probably easier to prove because essentially in general how you define injective and surjective maps in category theory is if you have a map, let's call it psi, you have psi of f equal to psi of g, and that implies f is equal to g. Then you say psi is a monomorphism. And so that's similar enough to regular injectivity, right? But then what's nice is looking at things this way, the dual notion of surjectivity is easier to see. Like this is essentially right function cancellative under composition. The dual notion of surjectivity, or being an epimorphism, you have right function cancellation property. So this says that psi is an epimorphism. So from this, by the fact that if you have an isomorphism, it is necessarily a monomorphism and an epimorphism, you can show that, you know, this has to be injective and this has to be surjective.
Wouldn't it
So-
be? Oh, never.
Did I have it messed up? I think that's right. I started to say one thing, but then I changed it. This is this has to be injective. This has to be surjective. So I'll probably just prove one, because once you see how to do one, you can see the other pretty easily. So let's show that alpha star has to be an epimorphism. In other words, in the category of top, a surjection. So we want to show,
It's 3 o'clock.
if you have two maps, F composed with alpha star equal to G composed with alpha star, that F is equal to G. So write composed with beta star, right? You get F composed with alpha star, a beta star is equal to G composed with alpha star, composed with beta star. In other words, F composed with psi is equal to G composed with psi. Psi is an isomorphism, so F is equal to G.
Yeah.
And so similarly, you can show this. And also they say a similar diagram arising from beta alpha homotopic to the one on Y shows that beta star is surjective. Therefore, beta star is isomorphism. Which shows that diagram commutes. Or wait. Well, no, that was our theorem. Our theorem was to show that beta star was isomorphism. So, let's see here. Next theorem. I guess I'll erase this stuff.
So basically, you draw these dual diagrams that pick up
Right, yeah.
surjectivity and injectivity.
You draw. Right, exactly.
One at a time. What's it? So if I'm just curious, Nathan. Epic. What's that mean?
Epic? Well, if you read Saunders MacLean, he distinguishes between an epic morphism and an epimorphism,
Oh,
but most people do not.
I see.
So I think for him, an epic morphism is a morphism that satisfies this criterion, whereas an epimorphism is a morphism in a concrete category where the underlying function is surjective.
Huh.
So because this abstract definition here doesn't necessarily mean that the actual underlying function has to be injective or surjective. That just happens to be the case in top. So there is actually a bit of detail I'm removing here, but I just wanted to show this method because
Yeah, sure.
I thought it was cool. So moving on to the next corollary.
I'll figure this stuff out when I teach my course on category theory here. It's cool. Hey, I can't help it. If the students demand it, I have to teach it.
So this is corollary 3.11. So this is a pretty nice theorem, pretty intuitive. If you have x and y path connected spaces,
So it's saying
with
that
the same homotopy type.
it just means that there exists a homotopy between them, right?
Yeah. Well, there exists a homotopy equivalence between them, which is what we used
Excuse me.
in this theorem here.
Okay.
So, same homotopy type. Then, for all x naught in x, y naught in y, we have pi 1 of x comma x naught isomorphic to pi 1 of y comma y naught. So the proof is basically just an application of theorem 3.10 and theorem 3.6, where we showed that the isomorphism class is independent of the base point. Right, because what we showed in the previous theorem is that essentially if you have a homotopy equivalence, that homotopy equivalence is actually an isomorphism. So two spaces that are homotopy equivalent are isomorphic under the pi 1 functor.
Pretty good.
So also corollary 3.12, I'm probably not even going to write. If X is a contractible space and X naught is in X, then the fundamental group of X at X naught is just the trivial group. So they say for this one, proof corollary 3.11 and exercise 3.11. Where exercise 3.11 just says that the fundamental group of a singleton space is just a trivial group. So now we have the definition we were talking about. So definition.
Really hard time teaching abstract algebra this semester. All my students are singletons.
All your students are what?
Singletons.
Nice. Okay, so if X
I don't know, what if they're watching this? Oh, I'm just kidding. They're all great.
is contractible
Anyway, we'll see you tomorrow.
and X naught is in X, then, oh, I was reading the wrong definition.
So, for example, the fundamental group of Rn
Now, what am I even doing? I started writing,
vector space.
no, I just started writing the theorem that I wrote down instead of the definition.
You're about to write down the thing you were going to write.
Yeah.
So space X is called simply connected.
If it's path connected and if the fundamental group of X at the point X naught is just equal to the trivial group for every X naught. So I guess I won't even bother writing it down at this point. Since my stupidity made me write down the other one. But so
It's funny.
the remark under here I think is
Why
enlightening.
Why for every X naught?
Why for every X naught? Well, because if you had, that's true.
Yeah, you only.
Yeah, you could get away with a weaker definition.
Yeah, do it.
If it wasn't path connected, saying for every X naught would make a difference. But since it's path connected,
Yeah.
you could equivalently say that as for any X naught. That's true.
It's in case we skip that theorem.
Yeah.
So I like the
You're
remark
right,
under
actually.
here. Essentially that just says that both pi 1 and pi naught are trivial when you act on this space. So that's an interesting way to think about it. So this next corollary here
Ooh.
kind of sounds pretty boring, but we're actually going to use it later. There's an interesting proof at the end. So
He says some authors allow for simply connected space to mean that it's like
So
pathwise simply connected. I mean component-wise simply connected, really.
oh yeah,
That's ooh, yuck. I don't like that.
so if beta from
Well, I guess
X
I would call it
X
locally
naught
simply
Mhm.
connected.
to y at y naught, it is freely no. Oh yeah. Is freely
Huh.
homotopic. So in other words, is homotopic to the identity on the space. Then the induced homomorphism beta star from pi1 of x at x naught to pi1 of y at y naught is trivial.
Wait, did you say homotopy to the identity?
Right, because it's not homotopic.
So Nathan, I know you're
homotopy to a constant, right?
Oh, thank you. Yes.
I know you're going on. This remark is fascinating to me. In complex variables, one calls an open connected subset U of the extended complex plane simply connected if its complement is connected. This agrees with our definition but requires some work to prove it. That's interesting. That means there's like a definition for simply connected and complex, which is non-homotopic. It's just in terms of connectedness of the complement. That's lazy. Anyway, I'm sorry. That is it's a completely separate discussion. That would be like, that really is something that should be brought up in complex. Anyway, go on.
All right. So essentially, we're showing if you have a no homotopic map. So essentially, something that's trivial because it's homotopic to a constant. Then the induced map is a trivial homomorphism. So proof of this is really easy. Let's see. K. So we have K be the constant map at y1.
I would have said the proof was trivial.
So we look at the induced map
Okay.
acting on F.
Okay. Yeah. Okay.
That's equal to K of F. But that's just a constant, right?
Right.
So up to homotopy. That's just equal to K.
Good.
So, wait, hang on. By lemma 3.8.
That's one with the commuting diagram.
Right. I'm just trying to see. Oh, okay. So what I was missing, we also have beta homotopic to K. So so we have, what is it? Beta homotopic to K and I guess K of F homotopic to K. Therefore, by the lemma, there's an isomorphism such that psi of beta star is equal to K star. So then, this was the easy part I was thinking of. I forgot some of the details. Once you have this, you know, invert the isomorphism, and you get beta star equal to K star. Oh wait, hang on.
You mean psi?
I
Psi inverse of K
I
star.
did the, yeah. So then this is a constant. Apply function to a constant, you get a constant. Therefore, it's bad, therefore. Map induced by beta is trivial. Alright, so we have finally made it out of the preliminary section.
Yay!
We are now to pi 1 of
It
S1.
only cost us 2 hours.
Yeah. So,
Of course, I will do much better in chapter 4.
chapter 4.
I am slightly facetious. It was a singular
Ah,
homology.
okay. So, let's see, what is it, 3:13? So I've got like half an hour. Might need to speed through some of this. Alright, so now we're actually, now that we have all the preliminaries, we're going to calculate, I say in quotes, more like derive, as I like the comment at the end. We have seen that computing the fundamental group of a space yields useful information, but this computation, even for S1, is not routine. In
Yeah.
other chapters, we shall develop techniques to facilitate this work. So, in other words, it's going to be fun trying to prove this. So, his first few paragraphs here, he talks about the winding number, which we talked about in complex. So, winding number of a path F from R to the complex numbers is defined to be 1 over 2 pi I times the integral around the path F of dz over z. So of course, as we learned in complex, this essentially calculates how many times you go around the unit circle. But I'll just go ahead here and rederive it. So essentially what they do, we rewrite f of t as, oh, okay, hang on. So one of the weird things they do in this section that confused me until I realized it, their definition of x is not e to the x, it's e to the 2 pi I x. Or I guess, I think they use s.
Oh my.
So
What the what?
that was confusing to me when I first went over that, so keep that in mind.
Yowzers. No, no, no.
So essentially what they do in order to solve this interval, and we're going to do
The first time I find myself disagreeing with Rodman.
No? Oh yeah. Like, isn't notation, it's sort of, it's like, some people use CX or like
Oh, the CIS.
CX.
I mean, there's a lot of different notations, but
Yeah, but
it's
this is
fine.
what he uses. So.
It is what it is. So we can do it.
So essentially, with this in mind, what he's going to do is make a substitution. F of t equal to the abhorrent x of
So there's this mysterious 2 pi I in the derivative of x that comes from nowhere.
right, exactly.
Yes.
So once you have that, calculating dz, realizing that this is the case, you can see that dz is equal to z times 2 pi I times f tilde prime of t
Right.
dt.
So that the z.
And so when you substitute that back
Right.
in,
2 pi I's cancel.
right,
Fundamental theorem of
the
calculus.
winding number,
Put 'em in.
1 over 2 pi I.
Actually, is f tilde real?
F tilde,
Okay.
what is F tilde? I think F tilde is from the reals. F tilde is from the unit interval.
Yeah,
to
that's
the reals,
reasonable.
Yeah,
2 pi I times.
because it's, yeah.
Yeah. Okay. It's what is it? It's omega basically. It's the angular velocity. I think.
Yeah.
You're fine. Oh, it's not that either. It's actually the frequency. Like omega t, you can write as 2 pi ft. So this is like this f tilde is really like the frequency of the circle.
Hmm.
But anyway,
They say it's essentially a logarithm. Yeah.
okay.
But anyway, that's just a mark they make.
Yeah,
So,
whatever.
like you were saying,
Go on. Cool.
once we go, these cancel out. Fundamental theorem of calculus applies. You get a real integral
Yeah.
from 0 to 1 of f tilde prime of t dt. Which fundamental theorem of calculus? Just f tilde of 1 minus f tilde of 0. So they say, for example, let f of t equal to e to the 2 pi I mt be the function wrapping I around s1 m times.
Uh-huh.
Counterclockwise,